The standard model of driving assumes a straightforward physical process. Your eyes perceive a stimulus, your hands turn the wheel, and your foot presses the brake. It is a simple visual motor loop. Yet over 1 million people die in car accidents globally every single year. The vast majority of these fatal errors are committed by individuals with 20/20 vision and flawless motor reflexes. The eyes see the hazard, the hands hold the wheel, but the collision still happens. Driving is an extreme, continuous stress test of executive functioning, emotional regulation, and working memory. When human driving fails, it does not fail randomly. Drivers make very specific physical errors based on highly predictable psychological deficits. By isolating these deficits, we can build a unified psychological framework. We can map exactly which cognitive and emotional bottlenecks in the brain cause a driver to speed, drift, or crash. Labeling these events as mere accidents ignores the data. There is a distinct neurological blueprint behind every collision on the road. We start by looking at the physical outcomes. On the right, we have 3 main categories of driving errors: speeding, crashes, and lane deviation with dangerous overtaking. The left side, the psychological causes, is currently blank. A modern driver processes a massive, overlapping flood of data. They must monitor moving vehicles, traffic lights, GPS audio, and dashboard metrics, all while moving at 60 miles per hour. To filter this data flood, the brain relies on its first critical bottleneck: attention and working memory. Simulator data reveals that a deficit here maps directly to an increase in crashes and lane deviations. Using speech-to-text software or glancing at a passenger's co-pilot display requires immense processing power, rapidly exhausting these cognitive reserves. When drivers are cognitively overloaded, they actually tend to reduce their speed and increase their following distance. The errors they commit are passive: delayed braking and drifting slowly out of their lane. This cognitive limit explains why novice drivers crash more frequently than experienced ones. Lacking a fully developed visual attention mechanism, a novice's brain spends its limited working memory processing irrelevant background cues, like billboards, instead of actively scanning for road hazards. When the brain's processing bandwidth is saturated, the physical control of the vehicle degrades. Cognitive capacity directly dictates spatial control. As drivers flow through traffic, they must maintain situational awareness. This is the cognitive ability to construct and update a persistent mental map of surrounding vehicles, including the ones hidden in blind spots. If a driver engages in a secondary task, even an intense hands-free phone conversation, the working memory required to sustain that invisible mental map is redirected, and the map collapses. Without that spatial awareness, drivers lose track of the proximity of other cars, leading directly to multi-vehicle crashes. Beyond immediate awareness, navigating a route requires perspective memory. This is the brain's ability to form an intention now and remember to execute that specific action in the future. A clear failure of perspective memory occurs when a driver reads a sign warning of a reduced speed limit ahead, understands the information, but forgets to execute the physical action of pressing the brake a few moments later. This specific memory failure accounts for many instances where drivers exceed the speed limit without any malicious intent. Adding this to our schematic, we see that perspective and long-term memory failures link straight to speeding violations. A significant subset of drivers exceeding the limit are not actively choosing to drive dangerously.
They are experiencing a failure to retrieve an intended action from long-term memory. Cognitive limits cause passive mistakes, but active violations, wherein driver intentionally breaks safety parameters, are governed by emotional and executive overrides. Traits like anger and impulsivity bypass cognitive control centers. Impulsivity drives up error rates across the board, while trait anger dictates uncorrected speeding and dangerous tailgating. The data shows that high impulsivity, particularly in male drivers, strictly correlates with executing dangerous, high-risk overtaking maneuvers on 2-lane roads. Anxiety acts differently. A highly anxious driver rarely speeds or attempts aggressive passes. Severe anxiety physically narrows a driver's visuospatial attention field and induces internal distractions that map directly to our final error category: collisions. The immense cognitive load of managing internal stress leads to delayed reaction times and dangerous hesitation, particularly in complex urban environments or during severe weather conditions. While an attention deficit happens to a driver, an emotional violation is committed by the driver. The psychological source is different, and so is the resulting physical danger. Because these cognitive and emotional nodes fluctuate naturally over time, a human being's driving risk profile completely inverts between the ages of 18 and 80. For young drivers, the active threat nodes are concentrated here. They experience high system failure in attention due to sheer inexperience, while simultaneously operating at their lifetime peak for chronological impulsivity. This combination of poor visual scanning and high risk-taking generates the most crashes of any demographic. But over decades of driving, those impulsive emotional nodes naturally power down. Older drivers adopt cautious, patient driving styles. Intentional speeding and aggressive overtaking virtually disappear from their behavioral profiles. At the same time, the biological hardware supporting working memory and visuospatial navigation begins to degrade. This specific cognitive decline increases the rate of crashes per mile driven. The errors shift heavily towards spatial navigation failures, such as misjudging the distance of oncoming traffic at intersections. Aging doesn't make someone a universally worse driver. It simply moves the origin point of their errors from emotional dysregulation to cognitive decline. This chart shows the completed unified framework. It provides a definitive blueprint of human driving behavior, mapping how perceptual, cognitive, and emotional factors feed directly into specific errors on road. The diversity of these psychological triggers prevents a single engineering solution from solving every driving error. A lane deviation caused by the working memory overload of reading a GPS requires a completely different intervention than a lane deviation caused by the trait aggression of tailgating a slower car. Medically, this blueprint indicates that older adults can utilize adaptive cognitive training programs to specifically preserve visuospatial processing, extending their safe driving years. At the policy level, researchers are advocating for targeted psychological interventions. In the United Arab Emirates, for example, there's an active push to screen for impulsivity traits as a mandatory part of issuing new driving licenses. As we transition to semi-autonomous vehicles, the software must be designed to accommodate these strict human limits, recognizing exactly when a driver's cognitive capacity is saturated and attention has wandered off the road. Safe driving is a delicate, continuous equilibrium between our cognitive capacity to process the world and our emotional capacity to regulate ourselves within it.